Hello everyone, my name is Jundong Xie. I'm a senior security engineer from Ant Security LightYL Lab. Today, I'd like to share my topic called New attack service in Safari, using just one WebAudio vulnerability to rule the Safari. Let's begin. Let me introduce myself first. I am a senior security engineer from Ant Security LightYL Lab. I graduated from Zhejiang University and was a member of AAA CTF team. My main research areas are binary fuzzing, browser security, and macOS security. I have on Safari, PDF, and many mobile devices in 3 Tianfu Cup from 2018 to 2020. Like-minded people are very welcome to join our LightYL Lab, and security researchers are also very welcome to submit vulnerabilities to an SRC. I will divide my speech into following 3 parts. The first part introduces the background of my WebAudio vulnerability research. The second part introduces how I discovered the vulnerabilities in WebAudio. And the third part introduces the whole process of Safari export. First, let me introduce the background of the research. In the past, Safari vulnerability researchers often focus on the DOM or JS engine, but some system libraries used by Safari, such as audio, video, font, and Zatic, haven't received enough attention. There are few successful cases using vulnerabilities found in these modules to break Safari. Due to the built-in heap isolation mechanism of Safari, the heap used by these system libraries is not the same as the heap where the DOM objects and JS objects are located. As a result, the auto bounce right vulnerabilities in these modules make it extremely difficult to override some key JS objects. These vulnerabilities are difficult to exploit along with the coordination of an info leak bug. But I found that there is a bug that can cleverly override JS objects by passing Safari's heap isolation, ASLR, and other defense mechanisms, and finally achieve arbitrary code execution. I demonstrated the attack at the Tianfu Cup International Cyber Security Competition hosted by the Chengdu Municipal Government of China, and successfully pwned Safari with only one shot. Then we come to second part, WebAudio bug hunting. The WebAudio module is a library and provides rich API for playing, encoding, decoding, and transcoding audio on macOS or iOS. We can first take a look at a classic audio playback process. Take MP3 as an example. First, we read an MP3 file from disk. Second, we analyze information such as sample rate, bit rate, duration, and Zatic, and split audio frames in MP3. Third, we decode splitted audio frame to get PCM data. Fourth, we perform sound effect processing on PCM data, such as equalizer, reverberator, and Zatic. This step is optional. Fifth, we decode PCM data into the audio signal. Sixth, we give the audio signal to the hardware for playback. We can see that the steps 2, 3, and 5 are all analyzing a piece of input buffer, which is very suitable for fuzzing. Apple provides APIs at different levels for these functions. Some frameworks in low-level services are mostly libraries that deal with hardware. We don't care about this. We are mainly concerned about the frameworks in mid-level and high-level services to see which services is more appropriate to build our harness. The following is a functional description of the middle-level and high-level interfaces. The numbers on the picture indicate which items in the flowchart correspond to each library. First, let's take a look at the interface of the middle layer. This one is audiophile services. It can read basic information such as sampling rate, bitrate, duration, etc., and spread audio frames. Let's call this process audio analysis. Complete the second step in the playback process. And this one is audiophile stream services, similar to the audiophile services, but mainly for streaming media playback. Second step of the playback process. This one is audio converter services. It does audio date conversion, corresponding to the third step in the flowchart. Then let's focus on the high-level interfaces. This one is extended audiophile services, a combination of audiophile services and audio converter services. And this one is AV audio player. It is an advanced interface which can complete the entire audio playback process, including local file and network stream playback, correspond to all the steps in the flowchart, except for step 4. If you choose an advanced service, such as AV player, we need to use a graphic interface, which is not convenient for fuzzing. Audiophile services, audiophile stream services, audio converter services, extended audiophile services are all good choice. For the second step, compared with audiophile services, audiophile stream services makes our fuzzing much more efficient. So we finally selected audiophile stream services. For third step, the audio decoding process, I choose extended audiophile services for fuzzing, which is relatively easy to use. Audio is not a new attack service. As early as 2017, Risks achieved several CVEs in audio. In 2019, he achieved 3 more. But other than that, less attention has been paid to vulnerabilities in audio. Before 2019, browser bug hunting was focused on modules such as JS and Watson. Then, let me briefly introduce the binary bug hunting technology I used on macOS. This year, Project Zero disclosed how they exploited the vulnerabilities in MHIO. They wrote an instrumentation tool called TrapFuzz for it. This tool is very suitable for library fuzzing, and the fuzz efficiency is pretty high. The harness needs to be carefully designed. The audio parsing step may be relatively simple. It can be divided into 3 steps: open, analysis, and close. But for audio decoding, various options need to be set for the output PCM format, such as sampling rate, number of channels per frame, number of frames per packet, etc. Since we want to increase the probability of reproducing our crashes in Safari, we should refer to parameter settings in it. Another important step is to collect as many seeds as possible. I have crawled hundreds of thousands of seeds from the internet, and then we can start enjoyable fuzzing. Achieved results. At present, we have obtained 16 CVEs in total, which includes 9 out-of-bounds read and 7 out-of-bounds write, and there are still tons of vulnerabilities in progress that have been submitted to Apple. CVE 2021-1747 is the vulnerability I used in this Tianfu Cup. I use this bug to achieve arbitrary code execution in Safari. Then let me introduce the cause of the vulnerability I used on the Tianfu Cup and the exploitation details. The vulnerability exists in AC Opus decoder append input date function of the WebAudio module, which will cause out-of-bounds write when passing CAF files. At position 1, there is a code similar to the bounds checking, but it does not take effect. And at position 2, the memory copy function is called, causing out-of-bounds write. Let me briefly introduce the CAF file format. Here, I draw a simplified version of it. The CAF file starts with a file header, and then is composed with various types of trunk. Each trunk has a trunk header, which records the size of the trunk. Disk trunk mainly stores some metadata of the file. This trunk stores all the packets, and packet table trunk records the size of each packet. During parsing, the packet table trunk will be read first to obtain the size of each packet, and then go to date trunk to read the corresponding packet. In order to analyze this vulnerability, I specially wrote a 010 editor template to parse the CAF file. This is part of the template's code. Then we analyze the CAF file that caused the crash and run it with the template file of 010 editor. You can see the following output. The first column is the size of the packet in both, and the second column is the first column is the serial number of the packet, and the second column is the size of the packet in both decimal and hexadecimal format. It can be seen that the size of the 114th packet is a negative number. It can be speculated that the program runs into a problem when processing packets with negative sizes. Because the code is too complicated and there was not much time before Tianfu Cup at that time, I did not conduct a detailed analysis of the root cause. Here, I mainly share my exploitation process. I first did a reverse analysis of the relevant code. The buffer written out of bounds exists in the structure called AC Opus decoder. The fields of this structure are as follows. The buff field is written out of bounds, which has a total of 1,500 bytes. The following fields such as buff size, controlled field, log object, and controlled are all controllable. This is a picture taken from source code of AC Opus decoder, produce output buffer list function. The program calls AC Opus packet get samples per frame first, and then it calls Opus packet pass input function. The return value is frame number. If the frame number is greater than or equal to 0, we enter the true branch. Then the program compares V37 and V23. If V37 is less than or equal to V23, we enter the true branch. In the true branch, program writes some value to addresses related to the log object. Next, we have two graphs. One is to go to the location while arbitrary address write occurs. And the return value must meet certain conditions. The other is to make the program not crash immediately after causing arbitrary address write. In the first step, we can do it by controlling the value of some variables. We need to ensure the return value of all pass packet pass input is greater than or equal to 0 to reach the point where arbitrary address write happens. This step is relatively simple. We only need to control the value of a few variables. Some twists and turns occurs in the second step. After an arbitrary address writing occurs, we find that the program always crashes in all post-decode frame function. According to the conventional analysis, if we want to achieve arbitrary address write, it will crash after write occurs. If we try to avoid the crash, we can't achieve arbitrary address write. But in the process of reverse engineering, I found a new bug. The function used for passing the packet does not check the length of the packet and will cause an out-of-bounds passing. So I constructed two packets that overlap each other. Let's look at this picture. Packet 1 is 2 bytes. The function used for passing assumes that each packet is at least 4 bytes. So it will be passed out of bounds to packet 2. The len x0xf8 in packet 2 is regarded as the one of the fields in packet 1. And finally, we avoid a crash and achieve arbitrary address write in the meantime. Usually, even with the ability to write arbitrary address, if the program's ASLR protection is done well, you have to find an info leak bug to exploit the vulnerability. However, there are some problems in the implementation of Safari's heap. We can spray controlled values on a fixed address by heap spray with arbitrary address write. The first thing that comes to mind is to override the length of the field in JS array, or the length field in array buffer. Due to Safari's GigaCage mechanism, even if the length field of array buffer is overwritten, we cannot read or write meaningful content. So I finally selected JS array. JS array in Safari uses Butterfly to store its length and content. If the length of the JS array is overwritten, then we can read and write out of bounds to the content of next JS array. Then two primitives, which called fake object and address of, can be constructed. The following two pictures are two different memory layouts that I encountered during the exploit. The left side is the picture, identifies the address of the memory. And the picture uses different colors to indicate that different types of objects are stored in different areas. I first tried to spray 2 GB of memory and found that my butterfly sometimes spray between 0x8 followed by 8 zeros to 0x1 followed by 9 zeros, and sometimes spray between 0x18 followed by 8 zeros to 0x1c followed by 8 zeros. Due to the heap isolation mechanism of Safari, different types of objects are in different heaps. Butterfly is in a heap called GigaCage in Safari. Some research on the GigaCage heap have found that the base address of GigaCage is predictable, and there are two types of GigaCage. One can store Butterfly, and the other can store array buffer. For these two types of heaps, GigaCage does more randomization. One situation is that Butterfly is on the upper side, and the other situation is that the array buffer is on the other side. Let's look at situation 1. Starting from 0x8 followed by 8 zeros. An unmapped area of 0 to 4 gigabytes will be randomly generated, and then the butterfly tip will be located below. In the second situation, starting from 0x18 followed by 8 zeros, an unmapped area will also be generated, followed by the butterfly tip. In either case, the degree of randomization of the base address is very small. I first tested it on a machine with 16 gigabytes memory. In order to spread the success rate, I spread 4 gigabytes. But later, I found that Safari monitors the memory used by each render process. If the memory used is too large, it will be killed. So I choose to spread 2.5 gigabytes finally, but this will cause the success rate to drop a little. But this is not a big problem. We are lucky to be able to trigger arbitrary address writing multiple times by modifying our CAF file to pull back the success rate. In order to facilitate the transformation of CAF files, I use ASM syntax to describe CAF files. ASM syntax supports the definition of various wise values, such as byte, word, dword, keyword, and also supports tags, placeholders, and repeating a value multiple times. This picture is part of my ASM file, which defines the CAF file header, disk trunk, some values used to trigger the vulnerability, and so on. The following sequence diagram explains the Intel export process. In the beginning, there was only one JS thread. We do heap spray first, and constructed the audio file in the memory. Then call the decode audio date function, which performs the audio decode process. Since Safari decodes the audio in a split thread, the audio A thread will be started here. Let's first assume that the memory layout of the heap spray is the situation 1 mentioned above. Then the audio A thread will trigger arbitrary address write for 3 times in the address range 0x8 followed by 8 zeros to 0x1 followed by 9 zeros when decoding the audio file, and the JS thread will detect whether the length of JS array is changed after 2 seconds. If it is changed, it means that we get the heap layout right, and then the subsequent express code can be executed. If it is not changed, it means the heap layout is situation 2. Then we call decode audio date function for the second time, start audio B thread to decode audio. This time we will trigger arbitrary address write in address range 0x18 followed by 8 zeros to 0x1c followed by 8 zeros. The JS thread loops to check whether the length of JS array is changed, and if it is changed, it will execute subsequent exploits. If it is false, it means that the entire exploit has failed. Besides, there is a problem that needs to be solved. After the audio file is decoded, some cleanup functions will be called. And since we corrupted the structure in a memory, a crash will occur. There are several ways to solve this problem. One is to repair the damaged heap, and the other is to make the audio decoding time very long, and make our exploitation process end before the decoding is over. The first approach is too complicated because we need to search the heap, and it takes a certain amount of time to repair the heap. The program may crashes when we are repairing the heap. So we choose the second approach. So we choose the second approach at last. I constructed a 600 megabytes CF file with more than 17 million packets. It will take about 50 seconds to decode all of these packets, which is enough for my exploit. After overwriting the length field of JS array, we can construct fake object and address of primitives. And then we can use Q primitives to construct arbitrary address read and write. At last, we write to the shellcode into the jet area to execute arbitrary code. These are all old school things, and I won't go into the details here. Audiences who are interested in it can read Project Zero's Celos article, Attacking JavaScript Engines, a case study of JavaScript core, and the CVE Q016 4622. My speech is ending. Does anyone have any questions?